SwayamPrabha. Digital India. Educated India.
I welcome you all to the session of thermal engineering basic and applied, and today we shall discuss about, rather we shall identify several factors those affect the nozzle efficiency, and then we shall solve one numerical problem on the flow nozzle. So, I mean before going to discuss about or identify those factors, so first of all we need to identify the factors which are very important considering their influential role on the efficiency of the nozzle, and then we shall discuss about their actual role. So, you know that it is better to write the nozzle efficiency that we could derive in the last class, that is the mathematical expression. What is the mathematical expression of the nozzle efficiency? So, if I write nozzle efficiency, and we could express mathematically as the actual heat drop that due to isentropic process. In other word, the actual gain in kinetic energy that due to isentropic process. So, basically if we write that is H 1 minus H 2 prime divided by H 1 minus H 2. So, this quantity that is the actual heat drop, right. So, that is not the, that is the real ideal heat drop, sorry. So, this is not the actual heat drop. So, this is the ideal heat drop, and this quantity is the actual heat drop. We also could relate this quantity to the velocity. So, if we write this, so this is again nothing but C2 prime square minus C1 square divided by C2 square minus C1 square. So, that is we also can write. So, basically this is the actual gain in kinetic energy of the steam at is as it is passing through the nozzle to that due to isentropic process. I am telling this is the ideal gain in kinetic energy of the steam as it passes through flow nozzle. So, that we also have discussed that this nozzle efficiency can be written like this. So, this we can write considering the fact that C1 is much less than C2, and this quantity essentially the what I can write, that is the velocity coefficient Kn square or psi square. So, this Kn or psi, this is the velocity coefficient, right. So, this is the velocity coefficient for the nozzle. Now, the value of this coefficient that I have discussed in the last class, that it varies from 0.93 to 0.97 depending on the surface properties of the internal surface of the nozzle. So, if the surface is very rough, then Kn will be I mean Kn would be little away from 1. If it is really relatively I mean smoother, then it should be closer to 1. So, you can understand that C2 square by C2 square. So, basically that you have studied in fluid mechanics, C2 prime square equal to Kn into so square into C2 square, or I can write this is C2. So, you know that you can see this relation that if Kn equal to 1, that is if the surface is atomistically smooth, then there is no frictional effect and the velocity, actual velocity is equal to the velocity that is obtained by considering the flow, rather by modeling the flow as an isentropic process. So, that is by modeling the flow process by an isentropic process. So, this is the case. Now, question is, having established the expression of nozzle efficiency, let us now look at what are the several factors those affect the nozzle efficiency. So, you can understand that in reality, so if we write that nozzle efficiency eta nozzle that equal to H1 minus H2 prime divided by H1 minus H2. So, this is the ideal heat drop, this is the actual heat drop, and also we can approximate, that is C2 prime square divided by C2 square. So, basically when there is a flow of steam through a nozzle or any channel, we have studied in fluid mechanics that frictional effect or frictional losses cannot be neglected, trivially neglected to be precise. So, the frictional effect cannot be trivially neglected, whatever the magnitude, frictional losses is there, frictional losses are there. So, basically that it depends on the fluid viscosity, it also depends on the surface roughness, surface properties. So, basically properties of the surface, rather bounding surface. So, when there is a flow through a confinement, that confinement is bounded by several surfaces. So, the properties of those surfaces also play an important role to dictate the frictional loss. So, what we can figure out today, now that we know friction tends to decrease the velocity. Why? Because that is the resistance. So, we have studied in fluid mechanics that if the surface is having roughness, it is because of this roughness, it is because of this roughness velocity of fluid very close to the surface is equal to 0. So, it provides a resistance to the flow. So, velocity will decrease. Not only that, it is because of this reason the temperature of fluid which is passing through a confinement will increase. So, basically it hits off the fluid basically which is being transported through the nozzle. So, what will happen, at least we have identified why I am talking about friction, because to model the flow through a nozzle we have assumed that the it can be modeled by an isentropic process. So, if we assume that the process is an isentropic process, we have considered that the frictional loss is absent, there is no heat loss from the flowing stream to the surroundings through the walls. So, basically we have considered first factor is the friction or frictional losses. So, factors those affect the nozzle efficiency, factors affect nozzle efficiency. Now, question is, so if friction increases, fluid temperature will increase, right. If fluid temperature increases, then heat drop that we have written over here, this is the ideal heat drop, but that we are not supposed to get. So, I mean depending on the case to case, suppose in one case surface roughness is there, in other case surface roughness is even more severe. So, if we consider these two cases, we will be getting relatively higher heat drop in the former case, while in the later case heat drop will be less, because more is the surface roughness, more will be the temperature of the fluid which is passing through the confinement, and heat drop will be less. So, basically increases fluid temperature and it decreases heat drop. This is quite trivial. So, basically if the temperature of fluid increases, then definitely the heat drop, that is, if we consider this is the confinement through which steam is passing or flowing, and suppose this is section 2 and this is section 1 and if the surface is very rough, so there is, and the nozzle surfaces are insulated. So, basically it is because of this insulation that is provided at the outer periphery of the nozzle, there is no heat leakage. So, our objective is to minimize heat transfer from the flowing stream to the surroundings, but it is because of the friction fluid temperature at the exit of the nozzle will increase. Suppose if it is temperature T1, this is T2. Now, if T2 increases because of this frictional effect, then T1 minus T2 will decrease. So, that is the decreases the heat drop. Not only that, this frictional effect will also try to reduce the velocity. So, it also decreases the fluid velocity. So, basically let us quickly review what is the effect of friction. Number 1, friction. So, if it is friction, so if friction increases, heat drop will reduce, velocity of steam at the exit will reduce. So, basically if we write this eta nozzle, that equal to H1 minus H2 prime divided by H1 minus H2, that is nothing but C2 prime square divided by C2 square. So, if friction increases, C2 prime will be lesser. So, the effect is eta nozzle will be less. So, efficiency of the nozzle will reduce. So, that means our objective should be to have a surface of the or internal surface of the nozzle, internal surfaces of the nozzle closer to a very smooth surface. So, it is very unlikely to have a surface which would be atomistically smooth. Our objective should be to have a surface closer to that one. So, that we can minimize the frictional effect, we can increase the fluid velocity at the exit, so that efficiency of the nozzle will increase. Our ultimate aim is to get higher fluid velocity at the exit of the nozzle, because we want to have a jet of steam. So, this is one. Number 2, let me discuss here. Number 2 is, see, this is basically something which is again related to friction. So, velocity. So, this is the main factor. Now, I will be discussing about velocity, but you can see the velocity is directly linked to the frictional effect. So, now what will happen, that if we increase, so if the friction is less, so when friction is less, right, why I am talking about, see, now question is, when you are talking about a nozzle, when you are talking about a flow nozzle, say this is the flow nozzle. So, this is section 2.2, this is section 1.1. I would like to write one important thing, that C1 is fixed because that steam is coming out from steam generator boiler, C1 is fixed. So, this is inlet condition. Okay. Exit pressure is also fixed. Right, and if we try to write, if we try to map the process in HS plane, so this is 1, this is P1, this is P2, so this is 2. So, the inlet condition 1 is fixed, process is isentropic, hence the outlet velocity C2 is also fixed. So, C1 is fixed, inlet condition is fixed, exit pressure is also fixed and process is isentropic, that means outlet condition is also fixed. That means C2 is also fixed. Right. Now, if C1 is fixed and C2 is fixed, because C1 is not there even in this expression, because C1, the magnitude of C1 is very less as compared to C2. So, basically from this particular from this analysis we can understand C2 is also fixed. So, if this is the fixed, so if we can place this C2 prime, perhaps we can modulate the efficiency of the flow nozzle. So, when friction is less, then fluid velocity will less. So, friction less means frictional resistance is less. So, velocity at the exit of the flow nozzle will be high. So, when friction is less, C2 prime will be more. So, basically when even we are talking about the actual case, even in actual scenario, if frictional resistance reduces, velocity, actual velocity will be more. So, efficiency eta nozzle will be more. So, if we try to understand the effect of velocity on the flow nozzle carefully, it is again directly related to the frictional effect. So, this is about 2. Finally, if we look at the last factor, that is 3, that is length of the nozzle. So, we have identified that if friction increases, C2 will reduce, efficiency will reduce. If velocity increases, that is again because of less friction, if velocity increases, actual velocity I am talking about, because C1 is fixed and C2 is also fixed, that is why I have written these 3 lines. So, if frictional resistance is less, actual velocity will be more, efficiency will be more. So, this is the conclusion. Finally, length of the nozzle. So, now let us see how we can relate this effect, we can relate this particular factor to the efficiency, to the frictional effect of the flowing stream. Say if length increases, we have studied from fluid mechanics that frictional resistance loss due to frictional effect depends on length, right. So, basically if length increases, frictional effect on the flowing stream will be more. If we have, so now we could relate the effect of length to the frictional effect. Now remaining part is straightforward. So if length increases, frictional resistance will be more. If frictional resistance is more, velocity at the exit of the nozzle will be less and efficiency will be less. So hence actual velocity C2 prime will be less, hence nozzle efficiency will be lesser. Why I am talking about actual velocity? Because to arrive at this particular point, C1 is fixed, that is inlet condition, right. Exit pressure is also fixed. Process is isentropic, hence C2 is fixed or C2 will be fixed. Okay, C2 is fixed, right. So that means inlet conditions are constant, that we have discussed in the last class. When someone is designing the nozzle, he or she also needs to know the exit pressure. Knowing the exit pressure, that means, and also you know the process is isentropic, because if we go back to the previous slide, so the process is isentropic. P2 is fixed, inlet condition 1 is fixed, and process is isentropic, that means velocity C2 will be fixed. So for a given value of C2, if length of the nozzle increases, frictional resistance will be more, which in turn will reduce the actual velocity of steam leaving the nozzle, and ultimate consequence is the reduction in nozzle efficiency that we have discussed. Okay. So with this, you know, we have discussed about the factors, we have identified several factors, those directly or indirectly affect the nozzle efficiency. What we have understood? Most importantly, we have understood that it is the frictional effect which is very important to be looked at while someone designing the flow nozzle, because it directly affect the heat drop. Nozzle efficiency is directly related to the heat drop. So we could relate the gain in kinetic energy to the heat drop using steady flow energy equation. So the frictional heating will increase the fluid temperature. So the actual heat drop in real applications will be less. So higher the frictional resistance, lesser will be the heat drop. If lesser is the heat drop, nozzle efficiency will be less. So this is what we could identify and we have discussed. So we have to stop today, and we shall continue our discussion with this problem in the next class. Thank you.